Okay, I'm back now. I hope you can hear me. Let me know if you can hear and if you can see. There's a live chat box that you can type to me in, so please do that. Kelsey, are you still there? I think everything looks good this time. Yeah, I think so. All right, so I'm gonna keep going, but again, Kelsey, if you're there or if anybody else is there, please type in the chat box and let me know if there are any issues. All right, so as I was saying before, we're talking about slopes of parametric curves and how to find the derivative without going to rectangular form. And so let's look at an example where we're going to analyze slope and concavity of a function. So in this example, the instructions say to find the slope and concavity for the curve given by and we have x equals cosine of theta. So in this case, the parametric variable is the theta instead of a t, but it still works the same way. And y equals sine of theta at the point where the parameter theta is equal to pi over 2. So we're going to use the formula that says that dy dx is equal to dy dt over dx dt, as long as dx dt is not 0. So what is dy dt in this case? So we're taking the derivative of y equals sine theta, so that's going to be cosine theta, and dx dt will be negative sine theta, the derivative of the cosine. And so what's the derivative at theta equals pi over 2? So dy dx evaluated where theta is pi over 2 is going to be the cosine of pi over 2 over the negative sine of pi over 2. Well, the cosine of pi over 2 is 0 and sine is 1, so we have 0 over negative 1, or 0. So we have a slope of 0 at that point. Now, the second derivative will tell us about our concavity. So the formula for the second derivative says that we take the derivative with respect to t of dy dx over dx dt. So be careful here. What is this saying? This is saying we're going to take the derivative with respect to, well, in this case, I should have written d thetas instead of dt's. Okay, so we're going to take the derivative with respect to theta of this function that we found here, which, by the way, could have been written as negative cotangent theta, over dx d theta, which we found already was negative sine theta. So a common error here to avoid would be, you don't want to just think that you can just take the derivative of the top function. If we go back to dy dx, you don't want to take the derivative of just negative cotangent of theta. You also don't want to take the derivative of cosine over derivative of negative sine. That would be incorrect as well. So we want the derivative of the whole function divided by derivative of x with respect to the parameter. So this is going to be let's see, the derivative of the cotangent would be cosecant squared, normally negative, but since it's negative already, it's going to be positive cosecant squared theta over, we still have negative sine theta. So cosecant squared is 1 over sine squared, so this is really negative 1 over sine cubed of theta, or cosecant cubed theta if you'd rather write it that way. But I like to think in terms of sine since we're going to be plugging in. So this is going to mean that our second derivative with respect to x, evaluated where theta is pi over 2, is going to be negative 1 over sine cubed at pi over 2. Sine of pi over 2 is 1, so that's just going to be negative 1 over 1 cubed, or 1. So negative 1. Okay, so this value itself doesn't have the same kind of meaning as the slope does, but it's the slope of the slope, right? So when we ask about concavity, we're not really looking for a number is what I'm saying. We're looking for whether it's positive or negative. So since it's negative, that means that we have concave down. Okay, so at that value where we've got a situation where we have a 0 slope and concave down. All right, another thing you might be asked to do is to find the points where we have horizontal or vertical tangent lines to the curve. So it'll say something like, example, find all points, if any, of horizontal or vertical tangency. To the given curve. So part A, we're going to look at the parametric equations x equals 4 minus t and y equals t squared. And so what would it mean to have a horizontal tangency? So we're talking about a horizontal tangent line, which means our slope is 0. So we're looking for a place where dy dx, which is, by the way, dy dt over dx dt, is equal to 0. So when is that going to happen? Well, that's going to happen when dy dt is 0, but dx dt is not 0. So when we're looking for a horizontal tangency, you can just analyze dy dt to see if it's equal to 0, but you also have to make sure that you didn't have an undefined denominator there. I mean, a 0 in the denominator making the derivative undefined. So let's check what's dy dt. dy dt in this case, derivative of y equals t squared, is going to be 2t. So when is dy dt equal to 0? So setting 2t equal to 0, we're going to say, well, that's when t is equal to 0. So when the parameter is 0, by the way, at what pair of coordinates would that be on our curve? You can find that by plugging into the formulas for x, the functions for x and y. So we're going to have, when t is 0, x is going to be 4, and y is going to be 0. So that would occur on our graph at 4, 0. Now, that is to say, as long as our dx dt is not 0, we still have to check that. So dx dt is actually just -1 in this case. So dx dt can never actually equal 0. So that tells us two things. One, it tells us that yes, in fact, this is a point of horizontal tangency. But it also tells us that we're never going to have vertical tangency, because vertical tangency would occur when we have 0 in the denominator. So when dx dt is equal to 0. So in that case, we are going to say, but the numerator is not. So that's never going to happen. So we have none. Okay, let's look at another example. Part B, same instructions, find all the values at which we have horizontal or vertical tangency. We have x equals 5 plus 3 cosine theta, and y equals -2 plus sine theta. All right, and we're only going to consider values of theta between 0 and 2 pi, because it's going to repeat after that. And so what are we going to look at? Well, first of all, keep in mind that our slope is dy dt over dx dt. And again, when the numerator is 0 but the denominator is not, we have horizontal tangency. So we're going to find our dy dt. So dy dt, the derivative of -2 plus sine theta, is going to just be cosine of theta. Well, I keep saying dt, but in this case it would be d thetas. So dy d theta would be cosine of theta. And so when is cosine of theta going to be equal to 0 on the interval from 0 to 2 pi? Well, if you remember your cosine curve, right, it's going to be at pi over 2 and 3 pi over 2. So theta equals pi over 2, 3 pi over 2. We'll have our zeros. And now let's think about dx d theta, because we need to make sure that those are not points where dx d theta happens to equal 0. So dx d theta, we're looking at the derivative of 5 plus 3 cosine theta. So the derivative of 5 goes away. Derivative of 3 cosine theta, we're going to have -3 sine theta. So when is that equal to 0? So again, remember your sine curve, right? So it's 0 at the ends and in the middle. So on the interval from 0 to 2 pi, we're looking at theta being 0 or pi. So what that means is that at pi over 2 and 3 pi over 2, we do not have an undefined denominator. We don't have 0 in the denominator, so the derivative is not undefined. So we definitely have horizontal tangency at these values, and also we're going to have vertical tangency at these. Since they're not, the numerator and denominator are not ever going to be 0 at the same time. So what points would these be? Well, so plugging in pi over 2 to our x and our y functions, we're going to have 5 plus 3 cosine of pi over 2. Cosine of pi over 2 is 0, so that's just going to be 5. comma, our y value would be -2 plus sine of pi over 2. Sine of pi over 2 is 1, so -2 plus 1 is going to be -1. So that would be one pair of coordinates. Another pair of coordinates would be, let's see what we get at 3 pi over 2. Pi over 2. So our x coordinate is going to again be 5, and our y coordinate is going to be -2 minus 1, so -3. All right, let's see where we have these points of vertical tangency. So theta equals 0 and pi. So plugging in 0, 5 plus 3 cosine of 0. Cosine of 0 is 1, so that's going to give us 8. And we have -2 plus sine of 0. Sine of 0 is 0, so that's just going to be -2. And then over here we have, for pi, again, we're going to have cosine of pi is going to be actually -1, so 5 minus 3 is going to give us a 2. And -2 sine of pi is 0, so that's just going to be -2 again. All right, so, but if you think about it, if you recall, we saw where these parametric equations of this form, they result in a ellipse. So if you think about what an ellipse is shaped like, if we're saying we have horizontal tangency at 5, -1 and 5, -3, so those would be the top and bottom of the ellipse, and then 8, -2 and 2, -2. Let's see, we're at 5, -1, here's 2. 2, -2 would be somewhere like here. So we'd have an ellipse, and we just found that we have 2 points of horizontal tangency and 2 points of vertical tangency, so that makes sense. Okay, let's look at another example. Part C. We have x equals cosine squared theta, y equals cosine theta. All right, so we're going to use the same procedure. We're going to, we're still trying to find any points of horizontal or vertical tangency. So we're analyzing dy dx using the formula dy dt over dx dt. All right, so let's go ahead and find these parts of the formula. So dy dt is going to be the derivative of cosine, which is negative sine. Oh, I did it again. We're using thetas, though, this time as our parameter. So dy d theta is negative sine of theta. And dx d theta is going to be the derivative of cosine squared, so that's going to be 2 cosine of theta times the derivative of cosine, which is negative sine. So we're going to end up with -2 cosine theta sine theta. All right, we need to know when each of these is going to be equal to 0. So first of all, when would we have negative sine theta equal to 0? So that's when sine is 0. Again, we're going to restrict our conversation to angles between 0 and 2 pi, because after that it's going to repeat anyway. So we're going to have sine of theta equals 0 at the ends and the middle of the interval. So that would be when theta is 0 and pi. And then for dx d theta, when is the product -2 cosine theta sine theta going to equal 0? Well, it's going to equal 0 when sine is 0. So we just mentioned that's when theta is 0 or pi. But also when cosine is 0, which means pi over 2 and 3 pi over 2. Okay, so what does that tell us? It tells us that at 0 and pi, we have an undefined derivative, but not a vertical tangency, because both the numerator and the denominator are 0. So we're going to have to, these values are not going to give us what we're looking for. So that means that there are no, and since there are no other places where dy d theta is equal to 0, then we have no points of horizontal tangency. Okay, but we do have a couple of places where the denominator of the derivative is 0, but the numerator is not. So in that case, we're going to have vertical tangency, and so that happens at pi over 2 and 3 pi over 2. So let's see what points those are. So for our x-coordinate, we need to plug into cosine squared. So we have cosine squared of pi over 2. And for the y-coordinate, just cosine pi over 2. So those are both going to be 0. So the point 0, 0 as a vertical tangent line. And then let's plug in 3 pi over 2. And we're still going to have 0, 0. So there's only really one place where we have a vertical tangent line, at the point 0, 0. And by the way, if you were to eliminate this parameter here by replacing the cosine in cosine squared with y, you would see that it fits the rectangular form x equals y squared. So what does that look like? That's going to be, it's going to be part of a horizontally oriented parabola. And the vertex of that parabola is at 0, 0. And so we can see why we have a point of horizontal, vertical tangency there at 0, 0. We would have a vertical tangent line. If you plot some points on the interval from 0 to pi, actually, it's going to start repeating after pi. What you'll see is that this is actually the part of the parabola that goes from 1, 1 down to 1, negative 1. And it just kind of keeps repeating. The orientation is this direction from 0 to pi. Okay, so just be careful if you see when you're doing these problems where you're looking for horizontal and vertical tangent lines, make sure that you do not use any points where both dy dt, or in this case dy d theta, and dx dt or dx d theta, both are 0. Okay, another type of problem that we might look at is we might be asked to determine open t intervals on which a particular curve is concave up or concave down. So let's look at an exercise like that. Example, determine open t intervals on which the given curve is concave up or concave down. Okay, so for part A, we're looking at x equals 2 plus t squared and y equals t squared plus t cubed. All right, so the first thing we're going to do is to find, since we're looking for concavity, we're going to need our second derivative. We're going to need to analyze our second derivative. So first things first, let's find dy dx. So that's going to be dy dt over dx dt. So dy dt is going to be 2t plus 3t squared. Dx dt is going to be 2t. Okay, and let's go ahead and simplify that. So that is dividing both parts by 2t. We're going to have 1 plus 3 halves t. As long as t is not equal to 0, it's undefined at 0. All right. Now remember to find our second derivative of y with respect to x. Oops. That's the same as finding the derivative with respect to the parameter of the first derivative, dy dx, over dx dt. All right, so our dy dx that we're referring to is this guy here. So as long as t is not equal to 0, we have the derivative of 1 plus 3 halves t is going to be 3 halves divided by dx dt, which we already found a minute ago was 2t. Or another way of writing this is 3 over 4t. And keep in mind that t cannot be 0, but luckily that's we have a little reminder of that here because we still have a t in the denominator. All right, so that's our second derivative, and we want to analyze it for concavity. So we want to make a sign chart, and we want to analyze where this is equal to 0 and where it's undefined. It will never equal 0 since there's a constant in the numerator, but it can be undefined at 0. So when t is equal to 0, our second derivative, which is 3 over 4t, is going to be undefined. If we plug in a negative number to our second derivative, 3 over 4t, that's going to be negative. And if we plug in a positive, we'll get a positive. So we can conclude that we are concave up when t is greater than 0, and we're concave down when t is less than 0. Okay, let's look at another one, part B, same instructions. We're going to analyze the concavity. The parametric equations are x equals 2t plus natural log of t, and y equals 2t minus the natural log of t. So we're looking for t intervals, values of t, for which we have concave up or concave down. When you're doing this, it's really important to remember to look for any restrictions on t. Like in this case, we're taking the natural log of t, so t has to be greater than 0. So you want to keep that in mind, because later on when we make our sign chart, we're going to disregard any parts that are not included in the domain. So let's go ahead and find dy dx by taking dy dt over dx dt. So dy dt is the derivative of 2t minus natural log of t. So that's going to be 2 minus 1 over t. And dx dt is the derivative of 2t plus natural log of t. So that's going to be 2 plus 1 over t. Let's go ahead and simplify this a bit. So multiplying through by t in the numerator denominator, we have 2t minus 1 over 2t plus 1. And we want our second derivative to analyze concavity. So now we're going to find the second derivative, which is going to be the derivative with respect to the parameter t of the first derivative, dy dx, over dx dt. So in order to do this, we need to take the derivative of this guy, dy dx, and that's going to be a quotient rule. So I'm going to write it down separately down here. So this part right here is this here. So we're going to find the derivative of that. So d dt of dy dx equals d dt of 2t minus 1 over 2t plus 1 is, we're going to do the bottom function 2t plus 1 times the derivative of the top, which is 2, minus the top 2t minus 1 times the derivative of the bottom, which is 2, over 2t plus 1 squared. Simplifying a bit here, we're going to have, let's see, 4t plus 2 minus 4t plus 2. So this is going to be 4 over 2t plus 1 squared. All right, so that's what's going to go into the top up here. Hold on, I need to move this guy a little bit. Oop. Come on, lasso. There we go. My lasso doesn't want to work. What's going on? Huh. Almost worked. Okay. All right, so we're going to write 4 over 2t plus 1 squared up here. And then in our denominator, we have dx dt, which we found before was 2 plus 1 over t. All right, so we have a bit of simplifying to do there. This is 4 over 2t plus 1 squared. And I'm going to think of 2 plus 1 over t. I'm going to think of that as 2t plus 1 all over t. So we're going to invert and multiply. So it's going to be t over 2t plus 1. So we're going to multiply by t over 2t plus 1. So that's going to give us 4t over 2t plus 1 cubed. Okay, so that's our second derivative, and we want to analyze it for concavity. So we're looking for intervals where t is t values that cause this to be positive or negative. So we need to analyze, where is this equal to 0? Well, it's equal to 0 when this is 0, so when t is 0. And it would be undefined if t with 2t plus 1 is equal to 0, in other words, at negative 1/2. But remember, the only things in our domain are things greater than 0. So what that means is when we make our number line, here's 0, we're undefined, and we're not interested in the stuff on the left. So we really just need to test one point and see if it's positive or negative. So if I plug in, say, 1 to 4t over 2t plus 1, we're going to get a positive value. So this is our second derivative sign chart. So we have that we are concave up when t is greater than 0. Okay, so another thing we want to do in this section is to talk about arc length, how we can find the arc length of a parametrically defined curve. So arc length so you might recall that we have a formula for arc length on an interval. If we have an interval from x sub 0 to x sub 1, and we have a function, y is a function of x, we would have that the arc length on that interval would be the definite integral from x sub 0 to x sub 1 of the square root of 1 plus dy dx squared dx. So what we want to imagine is that we're given a parametrically defined curve, we'll call it C, and it's represented by x equals some function of t and y equals some function of t. And so in this case then we know that dy dx is actually dy dt over dx dt, assuming of course that dx dt does not equal 0. So let's play with this formula a little bit so that we can write the derivatives in terms of dy dt's and dx dt's. So our arc length is going to become the integral from x sub 0 to x sub 1 of the square root of 1 plus, and we're going to have dy dt over dx dt, all of that squared, but that has the effect of squaring the numerator and squaring the denominator. Okay, and now what we're going to do is we're going to we want to write everything in terms of dt's, so what I would like is to have, instead of dx here, I'd like to get a dt. So I just want to point out that you can think of dx dt times dt as being equal to dx. So in the next step I'm going to replace the dx with dx dt times dt. And then that means I'm going to be integrating with respect to t. So instead of having bounds that are x values, we're going to switch them to bounds that are t values. So I'm also going to get a common denominator here and add this under the radical. So this is going to be the integral from t equals some number a to t equals some number b, corresponding to the x values x0 and x1. And we're going to have, we're going to get a common denominator here. So the common denominator will be dx dt squared. And then over here we'll have dx dt squared plus dy dt squared. And then over here, as I mentioned before, this we're going to write as dx dt times dt. So now if I take the square root of each part of this fraction, then the square root of the denominator is actually just dx dt, right? So we have the integral from t equals a to t equals b. We have the square root of dx dt squared plus dy dt squared over the square root of dx dt. So dx dt, I mean the square root of dx dt squared, so it's just going to be dx dt. Now, when I did that, I did make an assumption. I am assuming here that dx dt is positive. Dx dt, remember, could be thought of as f prime of t, and this only works if it's positive, because otherwise we get the absolute value of dx dt. But assuming it's positive, then we can cancel here and here. And so we have this handy little formula for arc length t from t equals a to t equals b, the square root of dx dt squared plus dy dt squared times dt. So in the next example, we're going to apply this formula for arc length. All right. So example, we are going to find the arc length of the curve on the given interval. And part A, we have x equals 3t plus 5 and y equals 7 minus 2t. And we're interested in the interval from -1 to 3, interval of t values. Okay, so writing down the formula for arc length, S equals the integral from a to b of the square root of dx dt squared plus dy dt squared dt. Okay, so before we can plug in there, we need to figure out dx dt and dy dt. dx dt is just going to be 3 in this case, and dy dt is just going to be -2. A and B are referring to the endpoints of our interval of t value, so A would be -1 and B would be 3. So we're going to have the integral from -1 to 3, the square root of 3 squared plus -2 squared dt. So that's the integral from -1 to 3 of the square root of 9 plus 4, so the square root of 13 dt. So the integral of a constant is just going to be that constant times t. So we have the square root of 13 times t, or t maybe be more clear to write t root 13. And we're going to evaluate that on the interval from -1 to 3. So we have 3 root 13 minus -1 root 13. So that's going to be 4 root 13. Hold on 1 second, please. Okay, so the length of the curve between -1 and 3 would be 4 root 13. So this one turned out pretty easy because the parametric functions were linear, so their slopes were nice and constant. This next one gets really complicated, so I'm saving, this is the last thing that we're going to do today. I just wanted to show you this one. Part B, we have x equals a square root of t, y equals 3t minus 1. And we're looking at t values between 0 and 1. All right, so first write down the formula. So we have s equals the integral from a to b, the square root of dx dt squared plus dy dt squared dt. All right, so let's find dx dt and dy dt. So dx dt is going to be, let's see, x is t to the 1/2, so it's going to be 1/2 t to the -1/2, and then dy dt is just 3. Oh, by the way, I forgot to mention on the previous problem, you notice that our derivative dx dt was positive, and in fact, in this case, this is 1 over 2 times the square root of t. That's also positive for all values of t, so on its domain. So in any case, that, remember, was an assumption that we made when we played with the formula here for the arc length. So that's good that we can use this. All right, now we're going to plug in. We have the integral from 0 to 1, the square root of, and then we have 1/2 t to the negative 1/2 squared plus 3 squared dt. All right, so let's see. We're going to have the integral from 0 to 1 of, this is going to be the square root of 1 over 4t plus 9 dt. Right, because 1/2 squared is 1/4, and this is really 1 over t to the 1/2 squared is just 1 over t. All right, so this doesn't fit an integral pattern very nicely. And so we can't, and I don't see a nice u substitution that we can do here. So we're gonna add these two fractions together. So we have the integral from 0 to 1 of the square root of, and then we're gonna have 1 plus 36t over 4t dt. I'm going to separate these two, the numerator and denominator, into separate square roots. So this is going to be the integral from 0 to 1 of the square root of 1 plus 36t over the square root of 4t, or in other words, 2 square root t. All right. So the first thing, this is a dt, the first thing I'm going to try to do here is to do a u substitution where I let u be, what I would like to happen is to get 1 plus u squared here. So I would like u squared to turn out to be 36t, because if I have the square root of 1 plus u squared, I can use a trig substitution. So that would mean that I would need to choose my u to be 6 times the square root of t, which we almost have, let's see, down here with the exception of the constant. So we're going to find our du. Let's see, du would then be, this is really 6t to the 1/2, so taking the derivative, 6 times 1/2 is 3t to the negative 1/2. Okay, so that's going to work out nicely because we have, this is really 3 over the square root of t. So our square root of t will be in the denominator, which is fabulous. We are missing our 3, and I need to bring that 2 out of there. So let's just do some rearranging here. So I'm going to put a 1/2 out front rather than having that 2 in there. And then I'm going to put a 3 here. So I'm going to need to multiply by 1/3 out here. Okay, and let's see. So then I think we can make our substitution. Oh, there's a dt here that I should have written. Excuse me. Okay, so we've got our dt, our square root of t, our 3. So du is represented here. So we're going to have the integral from 0 to 1 with a 1/6 out front. And we're going to have the square root of 1 plus u squared du. Okay. Now, I actually probably should, I can either just make a note that these are t values, or I can switch them to u values. It's pretty easy to switch them to u values, so I'm going to go ahead and do that. So when t is 0, u is equal to 0 also. And when t is 1, u is going to be 6, plugging in there. So let's go ahead and change this to 0 to 6. Okay. All right, so the next thing we're going to do is I'm going to do a trig substitution. When I have the form 1 plus u squared here, it would be good to use u equaling tangent of theta. So let's let u equal tangent of theta. So then our du is going to be secant squared theta. Now, if you're in my class, you're going to start recognizing this problem pretty soon. It's come up before, so something involving this trig substitution. So this is going to be the square root of 1 plus tangent squared theta. Keep in mind, these are u values now. I'm not going to switch them to thetas. And then a du, and again, I forgot my d theta here, is going to be secant squared theta d theta. Okay, so 1 plus tangent squared is secant squared. So this guy is the square root of secant squared, or just secant of theta. So going to the next slide here, we have 1/6 the integral from u equals 0 to u equals 6 of secant theta times secant squared theta d theta. Okay, so what you get here is 1/6 the integral from 0 to 6 of secant cubed theta d theta. The infamous secant cubed problem. So I'm not going to work through, oops, I wrote squared. I'm not going to work through integrating secant cubed. I'm actually going to refer you to Parametric JMT video. And let me pull up the name of that video for you real quick. I forget the exact title. I think it's integration by parts, a loopy example. But let me check. So what did I do with you? Here we go, YouTube. Parametric JMT. Integration by parts. A loopy example, yeah. So there's a Parametric JMT video. I'll try to add the link in when I upload this, or when I edit it, but just in case I can't. Integration by parts. This is on YouTube. A loopy example. Oh wait, but that's not just sine cube. Oh yeah, I think so. Well, this may or may not have this exact same one, but anyway, in our textbook, this problem was worked out in, I believe it's section 8.5. The integration by parts video by Parametric JMT shows how to what happens when the parts loops around, which this one will do. For the exact steps for this problem, look at example, it was example 5 in section 8.2. But anyways, it turns out to be the integral of secant cubed is 1/2 secant theta tangent theta plus 1/2 the natural log absolute value of secant theta plus tangent theta. And since this is a definite integral, we're going to evaluate that from u equals 0 to u equals 6, but we can't do that until we get this back in terms of u's. So remember that with the trig substitution that we made, right? Our u was equal to tangent of theta. Tangent of theta being opposite over adjacent, so u over 1. And then our third side is 1 plus u squared square root, our hypotenuse. So we also need to know what the secant of theta is equal to, and it's just going to be the hypotenuse over adjacent, so square root of 1 plus u squared. So what we're going to do is say this is 1/6, and then we have 1/2. Instead of secant, we have the square root of 1 plus u squared, and tangent is u. So u square root 1 plus u squared plus 1/2 natural log absolute value of the square root of 1 plus u squared plus u. All of this evaluated from u equals 0 to u equals 6. Okay, so I'm going to go ahead and bring this 1/6 inside. So we're going to have 1/12. U being 6, and then square root of 1 plus 6 squared is going to be square root of 37, plus 1/12, because I distribute the 1/6 again, natural log absolute value square root of 37 plus 6, and then that's plugging in u equals 6, and then we need to subtract from that, plugging in u. That's going to be 1/12, plugging in u equals 0, excuse me, 1/12, 0 times 1 plus 1/2 the natural log of square root of 1 plus 0. So all of this is just going to be 0. So plugging all of this into your calculator, if you want to get an estimate, this is approximately 3.249. Okay, so that would be like really extremely hard example of the integration that results, but you get the idea. We have everything from really easy ones like this guy to ones that are quite a bit more challenging, where we have to apply a lot of the different integration techniques that we've discussed throughout the semester. So I hope you found this video helpful. If you did, please remember to like it. And for my students, remember that you can get bonus points by posting a comment with a substantive comment, question, or quote. And it'll go in your D2L gradebook separately from your Test 4 grade, but it'll boost your grade. So thank you for watching.